We're going to take a look at a test that will help us determine whether or not a series converges or diverges. And this is one of our what's called comparison tests. So the idea for this is we're going to take a look at our series and then compare it to a series that we may know something about to try to determine, does that series converge or diverge? It's kind of simple. So here's kind of the visual idea behind this. So let's say that we have a series here, and I'm just going to mark our n's and a sub n's up here. So the idea here, let's say these are the a sub n values, right? So we got the sum n equals 1 to infinity of a sub n. So this would be, of course, here a1, a2, a3. So if I know something about this series a sub n, so let's say, because we got to look at this from two different methods, let's say that this converges, which means these values, all these a values here, add up to be a finite number. If I can compare this to another series, and I know that other series at every single place on here is less than that, then if I had this series n equals 1 to infinity of some other thing, if these b sub n's are all less than the a sub n's, if the sum of a sub n's converges, then the sum of the b sub n's would have to also converge, right? If all these values are less than all those values, those add up to a finite number, those have to add up to a finite number. Now we can look at this the other way as well. What if, let me say this, what if we know when we add up, what if I know when I add up all these values that these actually add up to infinity? That those actually diverge. If I had another set, and this doesn't work, I'll just do it red again. I know that we have these values here, and they're always above that. So if a sub n, if all those converge, when you add those up, if all those are bigger, those would also have to diverge. Okay, so here's the idea. We're going to take a look at our original series, and we're actually going to guess, does it converge or diverge? If we think it's convergent, then we have to show that each term here is smaller than our convergent series. If we think it's divergent, then we have to show that each term is bigger than our divergent series. So let's go ahead and put that into words real quick. So let's say, if let's say the sum n equals 0 to infinity of a sub n converges, and b sub n is less than or equal to a sub n for some n. So here's what we're going to say. We're going to say that the b sub n's are all less than some a sub n's after some point. They don't have to, it doesn't have to always be true, but at some point it has to be true and then forever. So let's say for n equals 1, this is false. N equals 2 is false. But n equals 3, and then forever it's true, this will work. So if this is true, then the sum n equals, let's do ones here, it doesn't really matter. Infinity b sub n also converges. So there's half of kind of the idea. We showed that if we have a series that converges, if every one of our terms is less than those terms, then our series with that will also converge. The other way around, if we know the sum n equals 1 to infinity of a sub n diverges, and we know that our b sub n's are greater than or equal to a sub n's, again after some value, then the sum n equals 1 to infinity of b sub n diverges. Okay, so it really has kind of two parts to it. And it's really based off of, do we think our original series converges or do we think our original series diverges? Let's take a look at a couple quick examples here. So, determine if it converges or diverges. Okay, so let's do something like, let's say we got the sum n equals 1 to infinity 1 over 4 to the n plus 5. All right, so our first guess here has to be, do we think it converges or diverges? Well, the easiest way to do this is let's really take a look at what this thing kind of ends up looking like as n's get bigger and bigger and bigger. So as n goes to infinity, right, as n gets bigger and bigger, our a sub n, which is 1 over 4n plus 5, looks like 1 over 4 to the n, right? Because that plus 5 isn't really going to matter when we get way out towards infinity. Well, what is this? What would this series be then? What's the series of n equals 1 to infinity of 1 over 4 to the n? Well, I can rewrite this. So this is n equals 1 to infinity, 1/4 to the n. Well, that's the series that we should recognize. This is a convergent geometric series. That's our convergent geometric series. Here our r is 1/4, which is less than 1, so that's why it converges. So we're going to think that this right here is going to act a lot like a convergent geometric series. So all we have to do is show that each one of these are smaller than each one of these, because each one, if you add up all these, they add up to a finite number. If all these are smaller, then it has to add up to a finite number. So what we're going to do is we're going to say for r's to converge, our 1 over 4 to the n plus 5 has to be less than or equal to 1 over 4 to the n. Now from here, you got a little bit of algebra to do to try to get to a statement that you believe is true. We have an inequality here, so we got to follow the rules of inequality. So if we clear our fractions or cross multiply, in this case, either way you want to think about it, we have 4 to the n is less than or equal to 4 to the n plus 5. Now remember, if you multiply or divide across an inequality, you have to flip it over if that quantity is negative. But both 4 to the n and 4 to the n plus 5 is always positive, well, forever, and of course from 1 to infinity. So we're allowed to do that without changing our inequality. You can see if we subtract 4 to the n to both sides, 0 is less than or equal to 5. So that's true, which means that this here is smaller than this here for every single value of n. So since these add up to a finite value, this adds up to a finite value. So since this is true, we can say that the sum n equals 1 to infinity, 1 over 4n plus 5 converges. Okay, so when you're trying to determine whether or not something converges or diverges, kind of look at the expression and say, what does that kind of simplify to as n gets really big? That'll give you an idea of what that series is going to act like as it gets really big, and give you a good thing to try to compare it to. All right, let's try another example here. Same directions, but we're going to run into a few problems on this one. Let's do the sum n equals 1 to excuse me, 1 to infinity, 1 over 2 plus the square root of n. All right, if we're going to do the direct comparison test or any comparison test, we need to determine whether or not we think that this is going to converge or diverge. So again, we're going to do the same kind of thing. So as n goes to infinity, our a sub n, 1 over 2 plus the square root of n, looks like 1 over the square root of n. If we take a look at that series, this will be the sum n equals 1 to infinity of 1 over the square root of n, or we can rewrite it like this if you'd like. 1 over n to the 1/2. This is a divergent p series. Here we got p is 1/2, which is less than 1. Okay, so this is a divergent p series, so we can kind of guess this thing here should act like a divergent p series. So my guess is this is going to diverge. So if I think that this is going to diverge, I need to show that these are bigger than all of these. So what I would do here is I want to show that 1 over 2 plus the square root of n is bigger than our series that we know is divergent, right? Because if all these guys add up to infinity, and if these are bigger, then those have to add up to infinity. All right, so if we do the same kind of thing, we can cross multiply here. Both of these are positive, so we don't have to worry about our inequality. Well, that's kind of ugly. Let's see, if we subtract the square root of n from both sides, we got zeros bigger than 2. This is false. Now here's where you're going to make one of your biggest mistakes. We said we thought that this diverged, but we got that it was false. That doesn't mean that it converges. It just means we didn't pick the right thing to compare it to. So false doesn't really help you out at all here. You're only looking for truths. So we compared it to the most obvious thing here, but it didn't work out for us. What if we compare it to something different? Now this is where you got to kind of get a little creative. So let me go ahead and get this out of here. So see, we know, I still think that this thing's going to diverge because it still should act like a p-series. Let's compare it to another p-series. We know the sum n equals 1 to infinity of 1 over n diverges, right? That's our p-series, p is equal to 1. Okay, we know that that diverges. Now, what if I compare it to that? Well, the same type of thing would have to happen. Our stuff here, our 1 over 2 plus the square root of n would have to be bigger than all of our terms in the divergent series. So we're going to do kind of the same type of stuff, a little bit more algebra this time. We can cross multiply, so that's 2 plus the square root of n less than or equal to n. Well, that's a little bit messy. The radical in there might be messing this up, so let's get that radical by itself. N minus 2, and let's square both sides to get rid of that radical. Maybe that'll help us see what's happening here. Well, that's going to be n's less than or equal to n squared minus 4n plus 4. Well, now that's just a polynomial inequality, so I can move everything to one side. N squared minus 5n plus 4, and try to solve this. Now, hopefully you remember how to solve this. The easiest way that I can tell you is, let's ignore the inequality part first. So really I'm going to just try to solve n squared minus 5n plus 4 equals 0. That's n minus 4, n minus 1 equals 0. So we get n is 4, n is equal to 1. All right, if we put those values on a number line, now we're going to check to see whether or not the inequality is true or false. Let's go ahead and put our closed circles because we have the equal sign. And we want to pick a test value from each region to plug into our original inequality and see if it's true or false. Well, if I pick a number over here, you can pick something like 0 or something like that. That doesn't really make sense because our series doesn't start until n is equal to 1. So this actually doesn't even really exist over here. So we can't pick a number over there. If we pick a number between 1 and 4, I don't know, let's pick 3 and plug it in our original inequality. So you can plug it in any stage. Let's see, what about right here? 2 plus the square root of 3 is less than 3. Well, that's not right because square root of 3 is 1 point something. So 2 plus 1 point something is not less than 3. So this is false right here. If I pick a number over here, I'm going to pick a perfect square. Let's pick 9. 2 plus the 3 is 5, is less than 9. So over here it's true. So notice here, this inequality right here will be true as long as we are bigger than 4. So kind of like way back over here, we just got to say that it's true for some value and always after that. So this will be true for every n value greater than 4. So this is, we'll come down here, true for n greater than or equal to 4. Now since that's true, what can we say? We can say since our terms are bigger than divergent terms, that our original series here has to diverge. So just for room's sake, so we can now say that this is diverges. Okay, this is the direct comparison test. You have to have an idea of what you're going to compare it to. The way you do that is just take a look at what it acts like as you head out to infinity. That should tell you whether or not you think it's going to converge or diverge, and then you need to compare it to a series that you know converges or diverges. Most of the time, the good news is what you think it acts like is what you compare it to, and you're not going to have too many problems. But every now and then, what you compare it to doesn't work out for you, so you have to be a little bit creative. Compare it to something else that you know something about. Pretty helpful test, so make sure you learn how to use it.